All right, I'm gonna start the material today and get going, no matter how many people we have. Basically, last time we went through parametric equations, converting parametric to rectangular and converting rectangular to parametric. Okay. And we saw the graph, and we also saw some really interesting graphs of parametric equations. Now, because I have these interesting graphs of parametric curves, these, obviously, if we wanted to do in a rectangular coordinate system, would be very hard to deal with. And they're much easier to deal with in a parametric system. And that's kind of what leads us into the next sections. We're going to do parametric equations with, I should say, we're going to do calculus with using parametric equations. And these parametric equations allow us to deal with curves that might not look very nice in rectangular coordinate systems, but look pretty nice in parametric systems. So that's the goal of today. All right. So we're going to do calculus things, calculus operations with parametric systems. And why would we do this? Sometimes the calculations are easier. Sometimes we deal with non-functions where we can't solve and get y equals a function of x. And it also, if we already have parametric, then we don't have to convert back to rectangular every time we want to do anything in calculus. Okay. So the first thing we're going to look at is the concept of a tangent. Well, when we were dealing with a tangent line in calc, hopefully you saw the tangent line as dy over dx, or change in y over change in x. So let's say we have a curve, whatever it looks like, and we're at a point here. Remember, the tangent line is basically the line going through that point whose slope is the derivative. All right. So the slope of the tangent line is the derivative at whatever point we're at. So the tangent line going through the point has slope, which is equal to the derivative of the function at that point. All right. And the derivative we think of as instantaneous change in y divided by instantaneous change in x. So slope, as we're following along our curve, think about a car driving along that curve. Once the car is at this point, if the car drew a straight line out from its headlights, it would be those headlights would be pointing in this direction, straight out. That's the idea. So it's instantaneous change in y divided by instantaneous change in x. And if we have parametric, then our y is going to be some function with respect to t. Oops, excuse me. And our x is going to be some function with respect to t. So if we have a parametric, instantaneous change in y is essentially just the change in y with respect to t. And instantaneous change in x changes into change in x with respect to t. In other words, the derivative of these two functions. Here. All right? So this is like f prime over g prime. Or excuse me, g prime over f prime, excuse me. Okay? So if we have this, then the derivative of y with respect to x, the way I've written it, I've written the g with the y, so it would be g prime over f prime. Okay, so that's the idea of the derivative. Now, in order to have the derivative at a point, we need to make sure we have a smooth curve. So we need to make sure that our curve is differentiable. And we need to make sure that our derivative of x with respect to t is non-zero because we don't want to divide by 0. Right? But let's take a look at an example. Let's say I have the parametric equations that you see there. X is equal to t squared plus 4t. Y is equal to 2t to the third plus 7t plus 8. Now, this is one where if we want to find the derivative, it's change in y over change in x, instantaneous change in y over instantaneous change in x. So all I have to do is take the derivative of this top, or of the y function. That's going to be 6t squared plus 7, and put that in my numerator. And then take the derivative of this x function, 2t plus 4, and put that in the denominator. And this allows me to find that slope of a tangent line as long as I know what t I'm talking about, right? For any value of t now, we can easily find the slope of the tangent line. Okay. So for instance, let's just go ahead and do an example. When t is equal to 1, we have x equals, well, when I plug in 1, I get a 5 for x. And y equals, when I plug in 1, I get a 17 for y. So in other words, we're at 0.117. Oh, I'm sorry, no, I apologize. I calculated there. Plug in 1 for t. I was looking at that as a 1, sorry. Or assuming I don't know what I was looking at. I should get a 5 for x. I apologize. We're at the point 517. I knew that sounded wrong. The slope of the tangent line at point 517 is what you get when you plug in a t of 1 into that derivative function. So that would be 13 over 6. So the slope of the tangent line at 517 is 13 over 6. And let's take a look at that on Desmos and see that it makes sense. All right. See that, hopefully, this makes sense. So let's start by graphing. We have t squared plus 4t as our value of x. We have 2t to the third plus 7t plus 8 as our value for y. Let's go from t of -2 to t of 10. There's my graph. Now, what we're doing is we're going to the point 517, this point right here. And we're saying that what's the tangent line? What's the slope of the tangent line? Well, a tangent line is going to be y equals m times x plus b, or, yeah, let's take m times x plus b. Where m is the slope. So if m is the slope, 13 over 6 is the slope. We just have to find the appropriate b. One way we can do this is that I know it goes through 517. So if I do y minus 17 on this side, and on the other side, instead of doing the b, I do x minus 5. We get that as our tangent line. This green one. And sure enough, it does look like that green tangent line is the correct line. It goes through 517. It looks like it's going in the same direction and at the same rate, at least at that point. Okay. So that's the idea. We can find those tangent lines. We can find slopes of tangent lines using slope of the derivative, dy over dx. Just like that. All right. Now, you can also do second and third derivatives too. It's a little bit trickier. Just like when you're dealing with so just like when we were dealing with rectangular coordinate systems, the second derivative is really the derivative of the first derivative. And the third derivative is the derivative of the second derivative. So in order to find my second derivative and my third derivative, I simply take a derivative of my previous derivative, if that makes sense. So to find the second derivative, I simply take a derivative of the first derivative. And when you take a derivative of anything, what you do is you take derivative with respect to t of whatever I'm dealing with, divided by dx dt. Derivative with respect to t of the second derivative, divided by dx dt. That looks messier than what it really is. So let's go through an example. Let's try to find the first and second derivatives of this. My parametric set of equations is x is equal to 4t, y is equal to 3t minus 2. And then it says find values when t is 3. We'll do that at the end. All right, so let's take the first derivative. First derivative is derivative of y with respect, or dy dx, dy over dx. Then I take the derivative of y. Now in this case, I get 3. Derivative of the x function with respect to t is a 4. So I get 3/4 as my first derivative. Now, what's going to happen on my second derivative? Is that this 3/4 is going to essentially behave like my new y. All right. And I'm going to take a derivative with respect to t of this function divided by derivative of x with respect to t. So on the bottom, I'm getting a 4 once again. And on the top, derivative of 3/4, that's actually just a 0, since it's constant. So second derivative is equal to 0. Now, when t equals 3, the derivative with respect to y, when derivative of y with respect to x, when t is 3, is just 3/4, or 0.75. And the second derivative, when t is 3, well, that's equal to 0. In this case, there's nothing to plug in, right? So there's really no calculations to do, just derivatives always 3/4. And if t was at 4, or t was at 2, or t was at -8, we would have gotten the same exact things. Let's do another one. Take a minute to try to find the first and second derivative in this case. By the way, the object you're going to get is a parabola turned on its side, like pointed left or right when you graph it. All right, I'm going to do it. I'm going to go through finding the first and second derivative here. First derivative, derivative of y with respect to t would give me a 4 on top. Derivative of x with respect to t gives me 2t plus 5 in the denominator. Now, I'm going to use this, but off to the side, well, I'll do this first, okay? Then what I'd have to do to find my second derivative is take a derivative of this expression and put it in the top. So that's basically, again, that becomes my new y. And my x is still my old x. So derivative of x with respect to t, I'm going to get, once again, just 2t plus 5. Now, let me do something off to the side. I'm going to write 4 over, this is kind of like my, in one sense, a y prime. And if I take a second derivative, or I take a derivative of this, what would happen is I'd get a -4 times 2t plus 5 to the -2, and then I'd have to multiply by the derivative of the inside function, which is 2. So I'm going to get -8 over 2t plus 5 squared when I take a derivative. So I'm going to do that one step here, but that's where it came from. So -8 over 2t plus 5 squared. So my second derivative, when I clean that up, is actually -8 divided by, well, if I have 2t plus 5 squared and I'm dividing by another 2t plus 5, that's 2t plus 5 to the third power. So second derivative is right there. Again, this is just a chain rule that we're utilizing. So I'm utilizing the chain rule to get that. You can go back and sort of review how to do derivatives, all that. But that's my first derivative. That was much easier to get. My second derivative is a little bit harder to get because I had to use the chain rule. But still basic Calc 1 topics. Now, when t is 0, when t is 0, we're at the point 4, 0. When I plug in 4 into x, or excuse me, when I plug in 0 into x, I get a 4. When I plug in 0 into y, I get a 0. So we're at the point 4, 0, and we're asking what's the first derivative when t is 0. I simply need to plug in 0 there, and you get 4/5, or 0.8. The second derivative when t is 0, well, I just plug in a 0 into here. I get -8 over, if I plug in a 0, I get 5 to the third. I'm just going to keep that as -8 over 125. You could give the decimal version of it if you'd like, but that's it. So we have first and second derivatives in this case as well. Once again, let's just take a look and see what that means as far as Desmos goes, and as far as the graphing goes and what we're actually finding. So we have t squared plus 5t plus 4, and then 4t. That's, oh, start with -10. That's this. We get a parabola, like I said, pointing to the right. Now, when t is 1, we were at the point 4, 0. Or I'm sorry, when t was 0, we were at the point 4, 0. So what we're saying there is that my tangent line is going to have slope of 0.8. And it turns out I'll have intercept of -3.2, but so now that's the tangent line. At the point 4, 0. So notice something about this parabola. This parabola fails the vertical line test, but we can still find the slope of tangent line for any point on this parabola. So even though it's not y is equal to a function of x, we can still find slope of the tangent lines. And as we saw, second derivatives we can find as well. Now, we wanted to figure out where we had vertical tangent lines or horizontal tangent lines. Vertical tangent lines have infinite slope. Horizontal tangent lines have 0 further slope. So if I wanted to take the stuff I just found and use it to find some vertical and horizontal tangent lines, Horizontal tangent lines have slope equal to 0. I know what the slope of all of the tangent lines are. They're my first derivative. So in this case, that's going to happen when 4 over 2t plus 5 is equal to 0. Now, it turns out in this scenario, that can never happen. So this can never happen. So there are no horizontal tangent lines. To this set of parametric equations. Now, on the other hand, vertical tangent lines happen at asymptotes. So we think of the slope being infinite. I'm not gonna be real precise on my language here, but the limit when it goes off to infinity. Think asymptotes. And that's going to happen algebraically when my first derivative does not exist because we're dividing by 0. So whenever you're dividing by 0, we're going to get the asymptote. I should say, in this case, when we're dividing by 0, we get the asymptote. There are times when you divide by 0, you don't get an asymptote, but if you don't have common factors above and below, then dividing by 0 is going to give you an asymptote. And in this case, that happens when t is -5/2 or -2.5 when you solve this. So we get a vertical tangent when t is -2.5, but we don't have any horizontal tangents on our graph. Let's make sure that happens by just taking a look at what Desmos has. Sure enough, it doesn't look like I have any horizontal tangent lines. There's no tangent. My direction is not going to be horizontal. There's no place where my tangent direction is going to be flat, perfectly flat. But at this point here, when you plug in -2.5, by the way, that point is -2.25, comma, -10. Right? At that point, we do have a vertical tangent line. Hopefully we can see that. If not, let me draw it. It'd be x equals -2.25. you get that vertical tangent line there. Drew my last tangent line in green, so I'll do that too. So I have one vertical tangent line. That's when t is negative 2.5. That gives you this point as your x and y values. And no horizontal tangent lines. Now, I want you to try this one on your own. Go back and just like in the previous example, find the first and second derivatives of this one. This one's a little bit easier to find first and second derivatives of. And then see what happens when the value of t is 0. And then if you have time, figure out if there's any vertical or horizontal tangent lines. All right, let's do it. Okay. So derivative of the y with respect to t is actually 1200 e to the t, because derivative of e to the t is just e to the t. Derivative of 20t is 20. So in reduced version of that, when you take 1200 and divide it by 20, you get 6. So this gives me 60 e to the power t. So with the second derivative, we're going to take a derivative of 60 e to the t. That's essentially my new y. So I'm going to take a derivative of that, and a derivative of that is once again itself. E to the t, derivative is e to the t. In the bottom, I'm going to take a derivative of x with respect to t, or you could have written it this way as well, derivative of t of my original x function. So my second derivative is 3 times e to the t. Now, when t is 0, we're going to be at the point 0, 1200. That's what you get when you plug in 0 into here. You get a 0 for x. And when you plug in 0 to here, you get 1200, 1200. So we're at the point 0, 1200. And my first derivative when t is 0, when I plug in 0 here, I just get 60 times e to the 0 power. Anything to the 0 power is 1, so 1 times 60 is 60. Second derivative, when t is 0, for the same reason, is going to be 3. E to the 0th power is 1 times 3 is 3. So we can get first and second derivatives, and if we wanted to, on this one, we could have gone and got the fourth derivative and the fifth derivative. Well, I should say third, and then the fourth, and then the fifth. Right? We just keep taking this as our new y. This becomes our new y when we go to get the third derivative. When we go to get the fourth derivative, we keep doing that same process. I'll take a look at this one. I'll do this one on the board. Oh, I forgot to say, on our previous example, there's actually no place where you get a horizontal tangent, and there's also no place where you get a vertical tangent, because e to a power can never be 0, and e to the power is never going to be undefined either. So you're never going to be dividing by 0, you're never going to be getting 0. So you have no vertical, no horizontal tangents on that previous example. So let's take a look at this. 2 plus secant of t and 1 plus 2 tangent of t. Now we saw last class period that this is going to be a hyperbola. And so we're talking about trying to find a derivative or the slope of a tangent line on a hyperbola, right? Secant tangent gives me the hyperbola. Derivative of y, well, derivative of 1 is just 0. Derivative of 2 times tangent, well, derivative of tangent is secant squared. So I get 2 times secant squared of t. Again, derivative of tangent is secant squared. Dx. Well, this constant, when I take a derivative, becomes a 0. Secant, when I take a derivative of secant, I get secant times tangent. Now let me rewrite that. 1 copy of secant on the top is going to cancel with 1 copy of secant on the bottom. And it turns secant divided by tangent gives you a cosecant. I'll show you why that is. Secant is 1 over cosine. Tangent is sine over cosine. So the short of it is cosines are going to cancel out. And you're going to get on top 2 divided by on bottom sine. One over sine is cosecant. So if we're willing to use our understanding of basic trig functions and canceling things out, this will simplify down to 2 times cosecant of t. Now for the second derivative, we're going to take a derivative with respect to t of 2 times cosecant. Again, this becomes like our new y. And the denominator is just the same old x. Now, numerator, when I take a derivative of cosecant, I get negative cosecant times cotangent. Derivative of secant is positive secant times positive tangent. Now you can rewrite all this stuff in sines and cosines, and it's probably going to look a little bit neater. So I'm going to go ahead and do that. -2 times 1 over sine times cosine over sine, all divided by 1 over cosine times sine over cosine. In order to get rid of 1 over cosine in the denominator, I'm going to flip it and multiply times the numerator. Notice that'll just give me another copy of cosine on the top. If I flipped this one, sine over cosine, and I multiplied it, I'll get another copy of cosine in the top and another copy of sine in the bottom. So when I flip and multiply both of those things, these two copies of cosine also go in the numerator. And I just get one big fraction. I get -2 times cosine to the third in my numerator divided by sine to the third in my denominator. This sine, and this sine. Cosine over sine is cotangent. So when all this is said and done, my second derivative is -2 times cotangent to the third power of t. So there you go. By the way, this one has a lot of places with vertical tangent lines because there's a lot of times when cosecant is undefined, when you get asymptotes in cosecant. It's everywhere where sine is 0, right? 1 over cosecant is 1 over sine. So whenever sine is 0, you're going to end up with vertical tangent lines. All right. So I know that's a lot of manipulation, but what that tells you is that there's a really, really quick way to find slope on a hyperbola, slope of the tangent lines on a hyperbola. And that's by using this first derivative, which we found to be 2 times cosecant of t. So if I'm willing to deal with parametrics, finding tangent lines on a hyperbola is really straightforward. Doing that with rectangular coordinate systems is much, much harder. Same thing here. This is an ellipse. If I want to find first and second derivatives of an ellipse, I'll go do this one on my own. So here x is equal to 5 cosine t minus 1. And y is equal to 7 times sine t plus 3. First derivative, take a derivative of y with respect to t. Derivative of sine is cosine, so we get 7 times cosine of t plus 0, because derivative of constant is 0. On the bottom, we'd be taking the derivative of 5 cosine t minus 1. Derivative of cosine is negative sine, so we get negative 5 times sine of t plus 0. There you go. By the way, this is negative 7/5 times the cotangent of t. Cosine over sine is cotangent. Second derivative, this becomes my new y. So I take a derivative of negative 7/5 times cotangent of t on top. And on bottom, I take a derivative of my old x. That's going to be negative 5 sine t again. Cotangent has derivative, which is negative cosecant squared. So that's going to create a derivative here. Negative of negative 7/5 is a positive 7/5 times cosecant squared. By the way, 1 over sine is cosecant. So you can write this a number of different ways. You can write cosecant as 1 over sine here, but I'm just going to say, oh, 1 over sine is another copy of cosecant. So that's actually cosecant to the third. And then the coefficient, 7/5 divided by negative 5, is going to be 7 divided by 25, and the negative of that. So now we see nice ways to find first derivatives and second derivatives with ellipses. This is much easier than trying to solve an equation that looks like this for y, and then taking a derivative with respect to x. Okay, this is this, and this give you the same curve, So if you want to find derivatives, much easier to use parametric in this case. Okay. And by the way, since cotangent is cosine over sine, there's a lot of different places where we get vertical asymptotes, and there's a lot of different places where we get horizontal asymptotes. Specifically, when this is 0, when cosine is 0, we get horizontal asymptotes. When sine is 0, we get vertical asymptotes. All right. Another calculus idea that parametric equations are pretty good at dealing with is parametric equations are good at figuring out the length of your curve. The length of your curve is called the arc length. So if we have two parametric equations, x equals f of t, y equals g of t, then the arc length, again, the length of the curve, can be found by integrating from a to b this square root. This square root comes from distance formula, and I'm not going to go through the origins of that because that was similar to the arc length that we did previously in this class way back when. So if we have a set of parametric equations, arc length can be found this way, integrating from a to b, f prime squared plus g prime squared, all underneath the square root. Now be careful here. This a and b, those are not x values. The a and b are done with, since this is all integrated with respect to t, those are t values. Okay? So be careful. A and b are both values for t, not x values. So let's do an example. Here's a curve that we want to find the arc length of. We have x equals 3t minus t squared, and y equals 2t to the 3/2 power. And we want to integrate that from 1 to 3. We're looking at the arc length from t value of 1 to t value of 3. Oops. So what you would do is you would turn to the formula. And I'm going to simplify this. I'm just going to go f prime. Some people will call this x prime squared. But the book and I call it f prime squared plus g prime squared integrated with respect to t. So the bounds are pretty obvious. Those are the t values, and I'm given the bounds in this case. I'm given, we're integrating from 1 to 3. We're finding the arc length from 1 to 3. F prime, F corresponds to the function in the x. So again, if you'd rather think of this as x prime, you can do that. Or derivative of x with respect to t, you can do that as well. That's going to be the derivative here, 3 minus 2t. And then I'm going to square that. Square the whole derivative. And then I'm going to go to g prime. Derivative of the y function is going to be 3/2 times 2 is just 3. T, and if I lower this exponent by 1, I get a 1/2 power, or a 0.5 power. And just like we had before, we've done this a number of times. We're just going to type this into our calculator. By the way, if you're in parametric mode, when you type in the random variable, key, you're gonna get the t value, you're just gonna see a t there. If you're in rectangular mode, you get an x, so you can use the variable, it's not a big deal, variable x, whichever variable you'd like, use. But we just type this in where t is the variable. So in my calculator, that's math 9, and then I integrate 1 to 3, square root 3 minus 2t, quantity squared, plus 3t to the 1/2 or 0.5 power, quantity squared with respect to t. And I get right about 8.86 as my final answer. So the length of the curve from t value of 1 to t value of 3 is about 8.86. Again, let's look at a picture. Just so we can understand what we're doing here. We're saying 3t minus t squared. And 2t to the 3/2 power. That gives you this kind of a weird looking curve, right? It's a little curl, and then it goes off in that direction. And if we go from t of 1 to a t of 3, we get that part of the curve. And we're saying that the length of that, if you made it a straight line and stretched it out, that length will be about 8.86 units. So that length is about 8.86 units. You can see it's going to be a little bit over 8 because, you know, the bottom piece goes from 2 and the top piece stops at a little bit above 10. So we know it's going to be over 8, but we don't know exactly how much over 8 until now, until we used calculus. And now we know it's about 8.86. Oops. Let's do this one as well. X equals e to the t power. Y equals 2t plus 1. So e to the t power plus 2, excuse me. Y equals 2t plus 1. Between t value of -2 and +2. So we're trying to find the arc length of this. Some people will write off to the side like f prime of t or x prime of t equals the derivative of this. And then g prime of t, which is our y prime function, is 2. So some people will write it off to the side. I tend not to do that. I tend to just write it in the actual problem itself. So what I do is I say, here's my arc length formula. I know I'm going to be integrating from -2 to 2 because that's what the t values tell me to do. And then I just replace the f prime in the formula with the derivative of this. And I replace the g prime with the derivative of g with respect to t, obviously. And at this point, I plug that into my calculator. Once again, if you're using parametric mode, this is a pretty straightforward process. Actually, let me show you in my calculator what I'm doing. Okay. So that was my previous one. But if you go into the mode and put yourself on parametric, what you would do is you'd go into math, number 9, integrating that. I'm going to go from -2 to 2. And then I take a square root in parentheses, E. And then when I hit this variable button, because I'm in parametric mode, it's going to give me the variable t. Plus 2 squared. And then when I hit the variable in there, it's going to give me a t. So I get about 11.89. Okay. If you don't want to switch into parametric mode, you can always do function mode and do the same thing. And just use whatever variable pops up. And function mode, that's just going to be x. But it doesn't matter which variable you plug in, your calculator is doing the same thing, and you get 11.89. Okay. So whichever one you like to do. Good to go. All right, let's go that way. Good. All right, so hopefully that all makes sense. So that's the arc length. Now, I want to go back and talk about a really quick thing. We were just dealing with a hyperbola and an ellipse. Okay, and just a couple of problems ago. And I know we don't have an example, there's no example 8 right there. But it's kind of an interesting exercise to find the arc length of an ellipse. So I'm going to go ahead and find the arc length of this ellipse. Now, if we're going to find the arc length of this ellipse, I have to decide what t values are going to go. And it turns out if you go all the way around the ellipse, this is an ellipse that's a little bit more vertical than it is horizontal. I'm overemphasizing that. But if I go from this point all the way around, you actually go from 0 to 2 pi. So the t, you want to go all the way around the ellipse, you'd go from 0 to 2 pi. Okay, that gives you a 360-degree rotation. Again, some people off to the side say, what's the derivative of this? And they'll write it down. What I'm going to do is I'm just going to go into my formula and say, since we want to find the arc length of an ellipse, we're going to integrate from 0 to 2 pi. F prime is -5 times the sine of t. G prime is 7 times the cosine of t. Don't forget to square those components. And then we're off to the races. Type that in your calculator, 0 to 2 pi. Integrate the square root of -5 times the sine of t. And again, all that's being squared, including the -5. Be careful about that. And then plus, in parentheses, 7 times the cosine of t. All being squared. Again, 7 is inside the parentheses, it's being squared. And when that's all said and done, you get about 37.96. So you can find the distance around the ellipse. And it turns out that all planetary orbits are ellipses around the sun. Now, the sun is not the center of the orbit, but it's actually one of the foci, right? So it's one focus of the ellipse. So all planetary orbits are that way. So you can figure out how far around the sun our planet orbits in a year using things like this. Okay, obviously the numbers are going to be much, much different than 5 and 7, but that's the idea. One other concept that parametric is really good to deal with is the surface area. Now, if you remember back to our earlier chapters, when we dealt with surface area, we rotated some piece of a curve around a vertical or a horizontal line. And for sake of ease, we're just going to either rotate around the x-axis or the y-axis. If I needed to rotate around a different horizontal line other than the x-axis, you could adjust it fairly easily. If you wanted to rotate around a different vertical line other than the y-axis, you could adjust that really easily as well. But basically what you do is you take your curve and let's say we want to rotate it around the x-axis. That would give me sort of a ghost image over here. I didn't draw it very well, but you can imagine. And what would the radius be? Well, the radius is how far from the x-axis we are up. Well, how far are we up? That's a measurement of the y value on my curve. So that distance is actually just the g of t. If I'm rotating around the x-axis. If I'm rotating around the y-axis, then the measurement is just the x value. And the x value is given to us by f of t. So it's a pretty straightforward formula. It's just the arc length formula where we multiply by the radius of our rotation. And if the radius, if we're rotating around the x-axis, then our radius is the y value. You can imagine if we try to rotate around another horizontal line, we just do y value minus whatever the horizontal line is at. And the same thing is true if we rotate around the y-axis. So that gives us our basic formula where we do 2 pi integrate essentially radius times arc length. And if we're revolving around the x-axis, our radius is going to be g of t. Remember, that's our y, that's the one associated with the y. G is associated with the y. And if we're revolving around the y-axis, our radius is f of t. And again, remember, f of t is the one associated with yeah. So it's 2 pi radius arc length integrated. Notice that the g of t and the f of t that are not underneath the square root are not being, that's just the original functions, not the derivative of the functions. So the pieces underneath the square root are the derivatives of the functions. But on the outside, these are not the derivative. These are our original function. Our original function for y and our original function for x. So 2 pi for the rotational, 2 pi radius, square root. So let's do an example. Here we have x equals 1/4 t squared. Oh, we're trying to find the surface area. So x is 1/4 t squared. Y is t plus 3. T is going to go from 0 to 3. And it says we want to rotate this arc length around the x-axis. So revolve this curve around the x-axis. So surface area formula is 2 pi. Integrate from a to b. Those a and b are t values. Since we're rotating around the x-axis, I'm going to go from x-axis up to my curve. That's a y value. So I'm going to do the y value, or g of t, square root f prime squared plus G prime squared with respect to T. Again, I'm using the G of T out in front because we're rotating around the x-axis. Most things are pretty straightforward. My integration is going from 0 to 3. My function is t plus 3. Now, when you type this into your calculator, make sure that this piece is in parentheses so that both the t and the plus 3 are going to get multiplied by this big old square root. All right? If you leave these parentheses off, then only the 3 gets multiplied by the square root. So make sure those parentheses are in there when you write out when you type in, I should say, your integration into your calculator. Then let's take the derivative of this. Derivative of this would be 1/2 t to the first, and then we're going to square the derivative. Derivative of this one is 1, and we're going to square the derivative of that. And we're going to integrate everything with respect to t, obviously. So again, inside the square roots, these are both derivatives. On the outside, that's the function itself. Now that we have it, we can simply type it into your calculator. Again, remembering to put parentheses around this. Just be careful. That we write it in an appropriate way. I got about 114.20. So that's the surface area. Maybe I should have said SA for surface area. That's the surface area of this curve rotating around the x-axis. 114.20. Again, that's just rounded to 2 decimal places. Now, what's going to happen if we revolve this around the y-axis? Well, if we take that same curve and we revolve it around the y-axis, then the only thing that's going to change calculation-wise is that as g of t in front needs to change if we're rotating around the y-axis into an f of t. F of t is my function that's giving me my x value. So the only thing I need to change is that function out front. All this other stuff stays the same. I'm still integrating with respect to t from 0 to 3. I'm still having f prime and g prime being squared and added together underneath the square root. I still have a 2 pi out front. And so we could type this in, 1/4 variable squared. And when I did that, I got about 21 21.49 as the surface area for the object rotated around the y-axis. So that curve rotated around the y-axis gave us a three-dimensional object, and the surface area of that object is about 21.49. Now here, I changed the variable up to use theta, but it's not that big of a deal. If you don't want to use theta, you can just use t in all your calculations. But I want you to take a minute and try to find the surface area generated by this curve around the x-axis. This is a strange curve. And again, it doesn't matter if you use theta or t as your variable. I'll use theta when I write things, but they're interchangeable. All right, let's go ahead and do this one. Like I said, I don't care if you use t's or thetas. This one is specifically put in there to show you that it doesn't matter what variable you use. The vast majority of parametric equations we use t for, but there are some that they might want to use the variable theta. All right, but all the same things hold. So if we're doing our surface area, we're going to be integrating from 0 to pi over 2. Since I'm rotating around the x-axis, the y value function is the one I need to put out front. Make sure you put parentheses around that whole thing. So that whole thing, theta plus cosine theta, gets multiplied by my square root. In fact, let me rewrite this just so it looks a little nicer. There we go. Now your f prime, that's your derivative of this. That's going to be 1 plus negative, 1 plus cosine theta. Derivative of sine is cosine. All right. Then derivative of our y is going to be 1 minus sine of theta. Or if you wanted to use t's as your variable. When I put it in my calculator, I put it in as t's, but. So we're getting 1 plus cosine theta all squared plus 1 minus sine of theta all squared underneath that square root. That's a lot to type in, but when you do type that in, make sure I did that, make sure I got all my parentheses right. I ended up with 23.24. Roughly. And so that's the surface area of this curve rotated around the x-axis. By the way, notationally, I know I'm kind of mixing up t's and thetas here. Notationally, that's hopefully not too big of a deal. Again, and I put t in there. Whoops. I should have put theta. We're integrating with respect to theta. I'm using theta. When I typed it into my calculator, all of these were just t's, so I just used t. Okay. Let's take a look at what that looks like via Desmos. So instead of doing theta, I'm just going to use t. So x is t plus sine of t. Y is t plus cosine of t. And if you go from, let's do negative 4 pi to positive 4 pi, you get this weird stair step effect where stepping, and it looks like it's a rounded stair, basically. Okay. Now, if you just take the section from 0 to pi over 2, that's just this little piece. So we're rotating that around the x-axis. That's going to give me some sort of a bowl shape, funnel shape. And that shape has surface area of 23.24 units, roughly. Okay. If you wanted to, you could find surface area of other things, like you could take a section of the ellipse and rotate it around the x-axis, or a section of a hyperbola and rotate it around. I'm not going to do that right now. We've done enough examples. of surface area, we can see some pretty interesting things. Okay. Now, instead of getting into 9.4 today, I'm going to stop and just conclude 9.3 in this way. Hopefully you saw that there's, with parametric equations, sometimes it's nicer to deal with calculus in parametric equation form than it is to deal with some of those calculus topics in rectangular equation form, right? Specifically with the ellipse and the hyperbola, you know, that first derivative was pretty straightforward to find. And with arc length and surface area, sometimes these parametrics are much nicer than the rectangular versions. Okay, this would be a really hard rectangular version to get out. So you can see how that would be advantageous. Other than that, like I said, we'll stop class today. We'll get into the next section, 9.4, next class. All right, so I'll see everybody then.